Hello everyone, welcome back to a new video. In this video we are going to make a racing game, the one that you saw at the start of the video. Alright, so let's get right into it. Okay, so now the purpose of the racing game was to program an AI, artificial intelligence agent, that will drive our car, the opponent car that we saw at as the red colored car. Right, now the basic mission of the whole game was to start from the bottom, the starting line, and go till the top, the finish line, and whoever reaches first is going to win the game. Along with that, we also had to avoid the obstacles that were present along the track. Right, now avoiding the obstacles is one thing and reaching it is another. As for us humans, it was really easy since we could see the car which were driving, and we were actually driving the car and we could see where we were going. But for an artificial or AI agent, it was difficult. So the technique that is used to avoid obstacles like the one we saw in the video was done using a technique called virtual force field algorithm. Right, so that is the one that we're going to discuss in this video. Right, so let's do this. Okay, so there were two parts to the AI car that we were seeing. If we assume that the AI car was over here, then the reaching the target over here is extremely simple. We can simply calculate the distance from the target to the robot or the character position, subtract the difference, get a vector which will be pointing along this way, something like that, and that could act. Now this along, after doing some scaling on this vector, multiplying it by some constant k or any constant, we could get the magnitude of this vector, and we could get the final force that we should apply or acceleration that this character should have to reach the target. Right, now reaching the target would be simple if there were no obstacles. It could simply go on like this and it would reach the target. But there was an added complexity of obstacles. Now, if we consider the character was somewhere around here and so there were some obstacles, something like this. Now, intuitively we would think that the robot should go across this way. But how does the algorithm work then? Now, within the radius of consideration, if we could consider something like this is the radius of consideration, the character would not consider the obstacles that are outside this, only the ones that are present inside this whole circle that we have. Now there are two obstacles that are present in this circle currently. What these obstacles are going to do, for the target we were getting an attractive force that was pulling the character towards the target. But for the obstacles we are going to exert a repulsive force that will push the obstacle away, the character away from it. Now this is going to be acting from the center of these obstacles and going something like this. Something along these lines, or yeah, something along these lines. And along with this, an attractive force would also be acting towards the target as well. Now summing up these vectors would give us some vector again in this direction. The final vector would be in this direction but some magnitude less, and the robot would start following this path. Now we can do this for any obstacles that we have. We can see that the overall vector is going to be in such a way that it avoids the obstacles as well as tries to reach the target as well. Okay, that's simple enough. But what is going to be the magnitude of these repulsion vectors? Now in order to calculate the value of the repulsion or the magnitude of these vectors, we are going to use something called the inverse square law. Now inverse square law is a general physical law that applies to any general body. We use it to calculate the gravitational force between two objects and the electric force between two objects. So it's a rather natural phenomena that we can see that uses inverse square law. We are going to use that over here as well. Now what inverse square law says, that if we consider this, the distance to be r, this force is going to be proportional to 1 over r squared. Right. Now there is going to be some constant that is going to be over here, k times r, k by r square, which we need to adjust. Now using this magnitude will give us the magnitude of the repulsion vectors. and we can then compute all the vector additions that we need to do, and finally follow the force that is being generated by the resultant of all these forces. Alright, that's good now. Okay, now this algorithm suffers from some problems. The most major one is it's a local path planner. What I mean by local path planner, it doesn't consider the overall picture of the complete map that it has. It will only consider the things that are in the vicinity of the object, of the character, and then decide a path that will take it through. Now this local path planner like this suffer from what we call a local minima problem. Now what a local minima problem would say, that if we have some obstacles like this and the target is just beyond these obstacles, then the character would not be able to pass. Now the overall resultant would come out over here. When it goes some distance away, it will again come up here, and some distance, then it will go down again, and it will keep on looping at this position forever. Now this is the problem that this algorithm suffers from, but that's it. Now one way to increase the capability of this local planner would be to complement this with a global path planner, something like A star, or any path planning algorithm like that. Then we can use that, the reference path that is generated by the global path, and avoid obstacles as they come along the path that we are following. Now that is one way, but the scope of our project is not that high. We just simply need a simple obstacle avoidance mechanism that can simply avoid the obstacles that are coming along the way. So that's why we are using this virtual force field algorithm. Right, now this is the complete picture of this algorithm that we discussed. Now let's jump right into the code and see how this algorithm is actually being implemented in the code. So let's do this now. All right, so here we have the code by the name kinematic separation. We could also name it virtual force field or something like that, but kinematic separation is just one way. The reason why this is, mostly in games, this algorithm is used for separating some people from the crowd. If, for example, if in a game we have a crowd that is moving and we want to make some distance between the people of the crowd, we generally use the separation algorithm, but we are using this algorithm over here by replacing some things and making it work for our game. Right, nothing big with that. Now, first of all, we are initializing the steering output that we need to produce. Now, the steering output over here refers to the forces that we are going to be applying. So we're going to have, currently we have 0 angular force, angular acceleration, and x. Now 0 is the x-axis force acceleration, and 1 is the y-axis acceleration. Right, now then we get the position of the character that we have, the AI agent. Then we calculate the obstacle state. Now kinematics stores the state of the obstacle, their x and y position. Then we can see over here that we're calculating the distance from the obstacle to the character, as simple as that. And then calculating the distance, Euclidean distance between them, by calculating the magnitude, right? If the distance is less than some distance threshold, the radius of influence as we discussed, then we can calculate. Otherwise it's less. If an obstacle is outside this distance threshold, then it is left out. But if it is inside the distance threshold, then we calculate the strength. This is the magnitude of the vector that we discussed. Now this is going to equal to minimum of the decay coefficient, the k, divided by r squared, distance times distance. And we're taking it a minimum because the distance times distance, 1 over distance square. If the distance is very close to 0, this value may blow up like completely. This will result in a very big value, and that will just make the system really unstable. We won't want that. That's why we are using this minimum operator to just stabilize the system and adjust the values accordingly. Then we are applying the x-axis strength or x-axis acceleration minus equals strength times the direction. Now we are not actually applying this along the y-axis. Like there is no such vector along y-axis. Now this is just an implementation detail, if we can say. This implementation detail is required because we want to avoid the obstacles either from the left or from the right. Our behavior doesn't need to be something like we are avoiding obstacles by stopping against the obstacle. We don't really want that thing. It's just an implementation detail. Other implementations can differ. This is my form of implementation of this. Right, after we are done calculating all the obstacle forces, then we are also, now this part over here, the L position, R position part, this is just to avoid the the AI car to go beyond the screen towards the left or completely towards the right. So it's just considering the force, it's considering that the left boundary is applying a force towards this place and the right boundary is applying a force towards the left. So that way, the AI agent doesn't just cross the boundary and go away from the screen. That we don't want. So that's why we're just doing this. Okay, now here is the target thing that we discussed. Now we are calculating the distance from the target to the character. Then we are taking the distance, taking the square root and all. And then we are adding that distance by applying some constants and normalizing and all. So we are calculating the force towards the target. And then we're returning that acceleration. And then this acceleration is being applied to the robot, the AI car, and the AI car moves accordingly how the forces add up and so on. So that's the complete overall algorithm implementation that we need to discuss. The other files that are present in this folder are required to make the algorithm complete along with the game. So if you want to check out this complete game folder or repository, the GitHub link is present in the description. You can check that out. All right. So also the complete game, you can compile the game and run it and see how well you perform against the AI agent that we have. And you can comment down how you performed, how did you win or not in the comment section below as well, right? Okay, so this is all what we had in this video. If you like the video, please press the like button and subscribe to the channel for more videos like this. Other than that, thank you for watching. Bye.